Alright guys, welcome back to Easy Math Made Hard. Today, to begin, we are going to be going over the little procedure that I talked about at the end of the video. If you need a refresher, it is to where you have an integral, like this, from 0 to a of, and then you can make it equal to any number that you want, entirely based off of a. So let's get started. So first we're going to have to go over some stuff. So let's say we have a function, g of x, and let's say it's equal to the double integral, but the last integral actually has bounds from 0 to a of f t. You technically don't need the double integral, but if you were to have just a single integral, you wouldn't be able to do all the fun of integrating. So let's say g of x is equal to 16. 16 is a very versatile number. It is a perfect square, and it's even, and it's relatively small. So a nice number. So it's equal to 16x. And let's say f of t is equal to something basic, 5x, right? And so we know that 16x is equal to the double integral, the second from 0 to a of 5. So let's just make actually just set dt. So 5t dt. All right. So now you can probably see what's going on now. So we know that the derivative of g of x is equal to the integral from 0 to a of ft. This is because a derivative is opposite of integral. So if you take the derivative of this, it just cancels out that integral. So now we have, and so the derivative of 16x is 16 because I've used the power rule. So let's put the 16 aside. So we have x1, this each other. So what you do is for the power rule, you take the exponent, since this is x to the first, and you put it in the back, and then you subtract 1 from it. So the derivative of x is equal to x0 times 1, which is equal to 1, and 16 times 1 is equal to 16. All right, so there you go. So 16 is equal to the integral from 0 to a of 5t dt. All right, so now we just do the opposite of the derivative. So we know the power rule, x1 minus 1, 0. I mean, my bad, 1 right here. And so if we do the opposite of that, so x1 plus 1 over 1, something like that. So just the opposite. I made a mistake with my anything. So look right here. So the integral of x is equal to x squared over 2. I'm going to make that what I had was, it was x squared over 1. This is because x to the first, so you add 2, or add 1, and then you put it over 2. This is because if you were to find the derivative of x squared over 2, what you would do was you would take x 2 multiplied by 2 over 2, because this could be represented as 1/2 x squared. So what you do is you have 2 x squared 1/2. We're going to use cancel out, and you have to subtract 1, so it's equal to x to the first power. So yes, there's not back at this. So the integral of 5x is 5x squared over 2, which is equal to 16 multiplied by 2. So 5x squared is equal to 32. 16 times 2 is 32. And then divided by 5. It's supposed to be a, by the way. So a squared is equal to 32. I think we're running like that. 32 over 5. And then boom. So 32 over 5 over 2 is equal to 16. And there we go. Now we were able to take, and so this works with any function. I just chose a basic function, so it was easy to integrate. But it works with literally anything, but it might be a bit more challenging to solve it after the fact. But yeah, so that's that. So we will most certainly be using this later, and finish my mic, so I could have died. It'll 100% be a very valuable thing to know. It is part of the fundamental theorem of calculus that I'm sure a lot of you guys are indeed might be familiar with, because I would assume that if you're watching this, you'd have a basic understanding of math, or you're one of my classmates who just likes to listen to me talk or something. I don't know. And so now let's go back to circles. They're very special shapes. So let's first start off with some light physics. So we know light polarization. So there's two wavelengths. So there's the electromagnetic wavelength, and then there's so light functions in the electric field and the magnetic field. So we can represent so they can be polarized in any direction as long as the fields are polarized perpendicular to each other. So let's say we have a vector field. So you know what a vector field is. So vector field is where every single vector has a specific direction assigned to it. So that's when you like see those lines with like arrows. I don't know how to do this special thing you would chuck go like this. Okay, super carried away. So vector field is where every single vector has a specific direction assigned to it. So but we will be focusing on a perfect vacuum. So let's say we have an electromagnetic wave right here, just any wave. that is going perfectly. So this wave would be coplanar to this whiteboard, which means that the other wave of the so this could be electric. Let's just say this is electric. So the magnetic wave would be directly perpendicular right there, so you won't be able to see it because it'll be coming out because it's perpendicular. So yeah, so you can also represent this. Let's say we have a sine wave that's facing towards us, so it'll be like just like a line, but as the lines but it'll be like going from its peak to its trough. So it'll be going like boom, 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 but the amplitude would have to be exactly the same. So yes, so we have a sine wave or cosine wave. We're going to use cosine, and there's going to be then this other, so the electric, and this is going to have to be right because they have to be directly perpendicular to each other if they are polarized with the same offset. I'm sure it functions the same if they're not, but it's just a bit harder to visualize in 3 dimensions, which is why we're working in 2 dimensions. Totally not because I'm limited to with the chalkboard. So let's say we have a function. So the function will be cosine. Well, no, we have a, which is going to be equal to its amplitude. So a for amplitude, cosine 2 pi f of x t plus phi, and this is called a ket, short for bracket, and this represents it as the vertically polarized part. Well, actually, since we're doing x, let's do it horizontally to keep it easier to understand. Well, technically, we're not doing it with respect to x, we're doing it with respect to t, which is time. So yes, so if we have a graph right here, cosine 2 pi is equal to 1, but since we have a function, it'll be like this. So it'll be like this, where this is equal to 1 unit. This little part right here. So it always the x-intercept will be 1, but t is represented to its frequency. So no, f is equal to its frequency. So as x increases, it will not change the amplitude; it will just change the frequency. So and a would be represented to how strong it is, how amplitude is, and then this phi would be represented to its offset. So it could be like offset by so much, by as much as you want. And so we have that for x, and we'll have the exact same thing for y. So let me just write that out. So notice how we're doing it to the vertical, because y is represented as vertical, but we're still doing it with t because it's our variable in the equation. So yes, but it'll still have the same thing, except in 3D space it would just be going in a different direction because it is polarized perpendicular to the x. But I hope this makes sense to you because it's a bit more hand wavy to my liking. So now we know that so as this oscillates, these two, so we have the two things that are coming out, but it's only in just one part. So let's just say it's like this part. So this, so say this is like 0 of the axis, the horizontal axis, and so then this would just be that. And so as this, so let's say these are equal, and we have, so these represents 2 waves. So as this goes right here, it'll look a bit more something like this. Because the amplitude for here, we're just going to keep those the same to keep it a bit. So, but if you were to add these two together, you would get a diagonal line. I'm going to redraw this. So the diagonal line, let's just represent this like this, so we're not dealing with annoying angles. And so then you would have it, and this would go out. So that's what would happen if you were to add them, and that would be equal to the radius of a circle that I'll get to in a minute. So, but if we offset these, so if they're offset, it'll be like, so let's say we have the x and then we have the y, and so the offset is equal to these two variables right here, because as you can see, it is going to result in a horizontal shift because it is in the same quantity as the x. So let's show you what will happen if you were to make phi x, so the absolute value of phi x minus phi y equal to 90 degrees or 2 pi radians, or pi 180 pi over 2. For some reason I started not maths in my fractions. Alright, so what would happen would be if ax is as big as it can be. So if ax is at its peak right here, then ay would be equal to 0. So hold on. So if ax is at its peak, then ay would be equal to 0. All right. actually this could be written as a biconditional, because a is at its peak if and only if y equals 0, assuming that this is equal to 90 degrees. And so what that will happen would be, so we have the y and the x would just be 0, but as x goes, assume that's the same length, because these two, we're going with the same, because this will only create a perfect circle if the amplitude is exactly the same. And then this would be 0. And so just assume everything in between in that, and then take the sum of these two to create the diagonal line. And believe it or not, this would trace out a perfect circle, assuming that the offset is equal to 90 degrees. So there we have it. And now we can find the area of that circle using some basic substitution. So let's go. So we know that ax cosine 2 pi f x t plus phi x horizontal ket plus a y cosine f x t plus phi y vertical ket. I don't think that's the correct term to call it vertical, but that's what I'm calling it. Would be equal to r. So there we go. And as and then as these, so since it's a cosine function, so as we move across t, so let's just represent that circle that's being traced on the little grid, and then of course we have the radius, and then this is equal to theta, right? And so as t progresses, for both of them, so let's just say we have the x I'm just doing this to represent these each go to the peak, so these are all going to be equal. And then we have the offset, which is equal to 90 degrees, or pi over 2. I'm just going to approximate the allocation. So if this is 1, and pi over 2 would be like, I don't know, it doesn't matter. It'll be like right here. Not really. And once again, the amplitude has to stay the same. And all right, so as t increases, as we move along t, theta will begin to increase, like so. And as we do that, we can figure out when theta is equal to 90 degrees. So when theta is equal to 90 degrees, we can simply integrate that using the technique we found in the last video, which is the trig substitution integral, which, yeah, that's about it. So believe it or not, this would be equal, so in the horizontally polarized thing, so when y, so anytime y, the amplitude of y is at its peak, so y would be at its peak if and only if x is equal to 0, because if, so let's just prove that this is biconditional. So let's say, so ay is at its peak, then a of x is equal to 0, and then if a of x is equal to 0, then a y would be at its peak. This is called the inverse. So yes, because you're just inverting it. Actually, no, it's not the inverse. Oh my god, dude. I'm literally just took logic in school. Like, I should know this. Oh, it doesn't matter. I don't need to get all fancy with my vocabulary. It's called the converse, by the way. So yeah, so when theta is equal to 90 degrees, so if theta is equal to 90 degrees, then, hold on, so theta is equal to 90 degrees if and only if a of y is at its peak. Alright, so if you need a bit of a visualization for this, it'll actually be, so y is at its peak and then is equal to 0, so it'll be 0 diagonal line, which means the diagonal line will be exactly equal to the vertical line, which is the radius, so the radius will just be equal to here, meaning that in relation to this axis, the x-axis, I guess, theta would be equal to 90 degrees, which is equal to pi over 2. And so now, what we can do is we can just simply represent this as a function. So, I'm not actually going to do that. I've already integrated that. I've already done it, and it's super annoying, and I get super worked up for some reason because it's just so cool. Because this is my first ever taken. I'm inventing math as we go along. And so that means hold on, I'm just gonna erase this all real quick because you've already seen it. Plus, there's a video that's recording right now. So it's equal to r, and if you integrate, r, wait, hold on, no, you can't just do that. You can't just integrate a line. So you can take the function 0 to pi over 2, because which is equal to theta, square root x minus r squared. Actually, I'm like super, I haven't done this in a while, but you get the deal. So yes, if you integrate that and then you multiply by 4, you should get pi radius squared. So this whole thing, and then if you were to integrate the function, the circle function, and use this value as r, and you plug in the values for this and stuff, then you multiply it by 4, you'll get pi radius squared. And pretty soon we're gonna do that, and we're going to do it so we can get a constant, a clean number. And I'm sure you already know how we can do that. It's just by a little bit of algebra. I did it in the last video, so we don't have to. I don't have to go over it right now. So yes, this concludes this first part of the first part. We're halfway done. Alright guys, welcome back, and we're just going to pick off where we left off about the radius of the circle. I just want it to be known that it is not the sum of the values these two produce that create the radius, because these two, we're dealing with vectors right now, so it's the location of these two vectors is where the vector of r is going to be, and then using that we can calculate using the distance formula to find it from the origin. So that's what we're going to do. So that might seem like a lot of work, but it's actually not. So the radius is just determined based on the amplitude of these two. So if this is equal to 1 and this is equal to 1 in a, which means a of x is equal to a of y because they're both equal to 1, that'll just mean that r will just be at 1 away from the circle. So let me write that out real quick. Equal to 1, and then once again, the offset has to be equal to 90 degrees. So since this offset will be equal to 90 degrees, we went over this in the last part, and I gave you a little bit of a visualization of how I don't mean that r is always equal to the amplitude. So we can just like get rid of this and this, so we just have the vector ax right here for the x part, and vector ay is going to be where r is. I'm using a bit of English because I don't know how you write this numerically in math notation. I could have just get rid of vector, less sensible. So now we're here. So and we know that a of x is equal to the amplitude, so we're gonna have to figure out what we want r to be. So let's take just like any value, like 100 for the area of the circle. So theta, let's theta, that's just burned into my brain. Theta. Answer goes equal to 100. That means r is equal to the square root of 100 over pi. This is because right there. Let's just solve it. Erase it. All right. So now we know that at any point this is gonna be the radius is going to be 100, square root of 100 over pi away from the circle. So the easiest way to do that was just make ax and ay is equal to the square root of 100 over pi. Because then therefore r will always be 100 over pi, square root of 100 over pi units away from the origin. All right. All right. Sorry. I'm still a little sick. I recorded the last bit like a week ago, and you heard me sniffing a lot. I'm sorry for that. So we know, so then we can just from here. So we already calculated r. We didn't have to use a distance formula or anything. So now we can just do we can just write it out. So the area. I'm gonna get rid of all this, and I'm gonna replace r with square root 100 over pi. So we know that square root 100 over pi cosine 2 pi f x t plus dx horizontal cap plus square root 100 over pi cosine 2 pi fy t plus y vertical cap is going to be equal to square root of 100 pi. Alright, so don't get into the fact that you just have to cancel this out and then that out. These are vector locations. They're not to be taken as numerical values that you can add and subtract. They're to be taken as distances away. No, not distances. They're just to be taken as points on a grid or plane. So we just know that so this is going to be a cosine, so it's going to oscillate. So that's the percent. So we know that. I'm going to write this out one more time. So no matter how many times you oscillate, no matter how many how forward or backward you shift t, the radius will always be equal to 100 over pi because the offset is equal to 90 degrees. All right. So now we just calculate this. So we take this and let's just give it a value. We have a value for it. That's what I was using in my word. We know that pi b squared is equal to 100. All right, so there we go. And we derive the area of a circle that will be traced out by a circularly polarized light wave functioning in both the magnetic and electric, just electromagnetic, that's the way light works. I don't know the proper word to use. I wanted to say spectrum, but like, I don't think that's the correct word. Anyway, so yeah. I wasn't gonna get into polarizing filters or anything like that. If you want, I could leave a comment. I'll figure out a way to integrate that. Unfortunately, not intended. I did not intend that. I'm gonna say I did now because it's humorous. But I'm gonna somehow integrate that into my thingy. So yes, if you enjoyed this one part, there's still gonna be more video obviously, but this is the part right here. Pi e squared is equal to 100, and we know that e is equal to all of this right here. So yes, I'm gonna function that into my main expansion. Anyways, see you guys in a minute. Hello, and welcome back. Please excuse my hair, water coach your hair. Anyways, we're gonna be going over 18 ways to calculate the number 1 to finish off this video. So we're gonna go from most commonly associated with 1 to the least commonly associated or unknown ways. So let's first start off with performing basic arithmetic to equal 1. Let's start off with 3 minus 2 is equal to 1, obviously. 5 minus 4 is equal to 1. 6 plus negative 5 is equal to 1. 5 divided by 5 is equal to 1. 3 I did that. Yes, I'm limited in the ways I can figure that out. Anyways, that's very obvious. Let's go on to number 2. Now I'll be multiplying a number by its reciprocal. Let's say 5 thirds times 3 fifths is equal to 15 over 15. This is true because you get the two numbers here because it does not matter which order you multiply anything in. So therefore, 15, 15, 1, remainder 0. We're going to get to this. Anyway, so yes, multiplying a number by reciprocal. Let's go on to number 3. Rise a number to the power of 0. So let's say we have 10 to the 0th power is equal to 1. Why is this? Well, we can start off with a factor tree. 25, 5, 5. So 25 is equal to 5 squared. See, right there. But we can also multiply it by any number times 1 to the first. That's also going to be equal to 1. So we can do this. So 1. I don't know how to explain it, but like it's just like okay, let's do another factor tree. So 100 can be written as 2 squared times 5 squared. You can also, but it makes sense they can do it times like 2 to the 0th power. Because you're just multiplying it by 1. I don't know, that's how I always visualized it. Anyways, let's move on to the next thing. 0 factorial. 0 factorial is equal to 1. Anyways, if you do not know what a factorial is, let's just say it's multiplied by all the numbers behind it. So 4 factorial is equal to 4 times 3 times 2 times 1. So yes, but here's something. So you can also multiply it times 0, but that won't work. So the 0 factorial is going to have to be equal to 1, because if you can multiply it by 1, that'll still satisfy the equation, which is equal to 24. Anyways, that's how you can visualize 0 factorial being equal to 1. In addition, we will be using all of these in our main expansion, so it is best to be looking out for these, so you know. All right, let's get back into the shapes for the next one. Finding a square, in which is area. Well, this one is very, very simple. Pretend those are 1. 1 squared is equal to 1. Next. Alright, finding a triangle where its area is equal to 1. I'm going to use a right triangle for this example. So, what we're going to have to do is it's going to have to be the square root of 1 for this one. Actually, wait, no, because you multiply these and divide by 2. So, we have to A and B. We're not going to get into the Pythagorean theorem. So, A times B has to be equal to 1. That means it has to be equal to 2, because the way you calculate the area is basically divided by 2. And let's just give this a base of 1 right here. So 1 times B is equal to 1/2. This one is very simple. Just divide it by 1 right here. So B is equal to 1/2. Therefore, pretend that was B. I was wrong. So 1/2 times 1 is indeed equal to 1. But you can also do this for other stuff. Like let's say 3. 3 times A is equal to 1/2. 3, 3. So A is equal to 1/2 over 3. And let's just check this out. 1/2 over 3 times 3 over 1. 3 times 1/2, we're going to write this again, is 3 over 1 times 1/2, because you can just write this as 3 over 1. And so what that will be is 2/3, 3 halves. So this will be 3 halves over 2, which is equal to 1/2, I believe. I don't know this yet. Well, let's see. 1 1/2, that's 3 halves. 1/1/2 over 2. You can write this as 1 plus 1. This can cancel out. I don't know if I'm doing this correct. I never take an algebra 2 as to your surprise. Which is equal to 1/2 over 1, which is equal to 1/2. I guess it works. Who cares? You know there's a way to find the area of a triangle or the area of a triangle. Anyways, let's go on to the next one. Alright. Circles. Area of a circle is equal to 1. Well, this is easy. Pi r squared is equal to 1, because that's the formula to a triangle. So it is just r is equal to the square root of 1 over pi, and if that satisfies it, so pi square root of 1 over pi squared, square root cancels out, so we have pi 1 over pi, that cancels out, so we have 1 over 1, which is equal to 1. Pretty simple stuff right there. Let's go on to the 8th thing, the first derivative of x. The derivative of x, so derivative is finding a slope at an infinitely small point, so x, y, oh god, I'm gonna let Andy do this right now, y equals x, y equals mx plus b, easy stuff, intersect is nothing, so we can cancel that out, so y is equal to 1, x, there goes to the derivative, x is equal to its slope at 2 points that are infinitely close together, represented by d. So then, you must understand that if x equals 1, the slope, since it's 2 points that are infinitely close together at a straight line, it doesn't matter how close you get, the slope will not change, so the derivative of x is equal to 1. Alright, another way to assume this is using the power rule, so what you do, x1 and you subtract, so you add the x1 there and you subtract 1, so it's 1, that's x to the 0th power, and once again, anything to the 0th power is equal to 0, there's another good way to visualize it, so 1 times 1 is equal to 1. Anyways, there's 8, on to the 9. Alright, this one anyone who's taking pre-calc will probably be able to understand this. This is a logarithm to its own base. It's equal to 1. This should make sense because, let's say natural log. Let's go with natural logarithms real quick. Ln of e is equal to 1 because ln x is equal to 1. All you have to do to get the x by itself is put e at the bottom, so e to the ln and e to the 1. So x is equal to e to ln e is equal to 1. This works for any other thing. Let me show you real quick. Let's go log base 10. Is equal to 1. Once again, let's go 10 to the first. Log base 10 of 10 is equal to x, and x is equal to 1. So once again, a log into its own base is 1. Alright, integrating function equals 1. Once again, integrals. We're going to do what we did in the very beginning of the video, right here. G of x is equal to 1x, or just x, so then g prime x is equal to 1. Once again, to the thing we said before, and then f of t is equal to, let's just go 10x, just an easy little integral. So g x is equal to the double integral of the second from 0 to a of 10 of f t dt. Once again, I have to make this next. I mean a t because that's a t. Alright, that means that 1 is equal to the integral from 0 to a of 10 t dt, and let's integrate it. So t to the first, so it's going to be plus 1, and we have to put it over 2. This is because the derivative of t squared over 2 is going to be, so what you do is you have to subtract 1 and multiply by 2, and that's going to cancel stuff out, so that's going to be equal to t, because an integral is an opposite of a derivative, as you saw right here, and in the beginning of the video. So that means that 1 is equal to a squared, 10a squared over 2, ranging from 0 to a, or, which we already did, that's why a is plugged in. Anyways, so 10a squared is equal to 1/2. That means that, and 10, so a squared is equal to 1 over 20. Just so you know, in the beginning of this, I'm sure you guys caught it, and I'm about to reward you for listening this far. I did like, so what I did was I would write this out, and then let's say I had 5x in that one, so I would do 1/20th squared, even though that's already squared, so I squared the square root of that to cancel it out. Don't worry, I caught it. I'm probably too lazy to fix it. Anyways, 10, 1/20th, we're not going to square it again, over 2 is equal to 1. Once again, let's solve. 1 over 20, so this is going to be the same as 10 over 20, which is going to be 1/2. So it's going to be 1 over 2 over 2 over 2. And just so you know, if you divide 1/2 divided by 2, let's do that right now. 0.5 divided by 2. Wait, hold on. Wait, hold on. Just so you know, 0.5 divided by 2 is equal, or 2 divided by 0.5. 2 times 0.5. Look, this is equal to 1. This should be very obvious, because 1/2, 1/2, why am I really bad at helping explain complex fractions? It's not that hard to understand. 0.5 over 2. Shouldn't that be 4? I don't know, hold on, give me a sec. Oh, I know what I did. I solved it wrong. So it's going to be 10a squared is equal to 1. It's over 2, so you're going to have to multiply this by 2. Cancel that out. So 10a squared is equal to 2. I'm just making so many mistakes at this point of the solving. Like, it's not even complex math. Then look, 10a squared is equal to 2/10. They're easy. So then we have 10 times 2/10 over 2 is equal to 1. And this is, so this can be written out as 10 to tenths is the same as 20 tenths. This is because it's multiplied by 2, which is equal to 2, and then 2 over 2 is equal to 1. There we go, I finally did it. Yes. For some reason, it's always a simple math that I choked you up. Anyways, there we go. We integrated a function where it is equal to 1. There we go. Now let's move on to the next thing. Yes. 0.9 repeating. It repeats forever, all right? So I'm going to try and solve this. I have a vague understanding how you can solve this to be equal to 1. However, I'm not entirely sure, but we're going to learn along the way. If in case not, I'm just going to tell you that if 0.9 is not equal to 1, what my math teacher said, that means there's going to have to be a number between 0.9 and 1. But there isn't. There is no number between that because 0.9 is going on forever, so you can't put a number in between that is not already part of that set, or whatever you're going to call it. Anyways, there we go. So 0.9 bar is equal to, let's say, just a t, I don't know. Let's multiply this by, supposed to multiply by 10, I think, so 9.9 bar is equal to 10 t. There we go. And then what you're supposed to do is you're supposed to subtract 0.9 from it. So minus 0.9 bar minus 0.9 bar. Let's do this real quick. 10. We're just gonna go pretty far, but you understand. 0.9999. These both are gonna go on forever. So subtract. All right, 0, 0, 0, 0, and this is gonna have to go on forever. So this is also gonna be repeated, and this is gonna be 9. So this is 0, so 9. Right here, so you have 9.0. So now we have 9 is equal to 9t. Divide both sides by 9. We have 1 is equal to t, and like we said, 0.9 repeating is equal to t. So therefore, 0.9 has to be equal to 1. So I guess I was correct on how to solve it. So there we go. There is a proof that 0.9 is equal to 1. Let's move on to the next one. Oh yes, cosine 2 pi. I don't know. I can prove this to you. Cosine 2 pi is just equal to 1. Everyone who's taking trigonometry should know that. Same thing with sine. Wait, hold on. That's the next thing. Yes, I'm not going to go over the proof. That's just common knowledge because I also don't know how to prove it. That doesn't involve a lot of math. Once again, totally just double check. Sine pi over 2 is also equal to 1. You guys want to see something kind of cool? No? All right, I'm joking. Sine pi over 2 minus pi. Well, let me check that. Let me just check that real quick. All right, so I was wrong. I'll put this much real quick. Let me rewrite this. So sine of x minus pi over 2 minus pi is equal to cosine x. So therefore, sine 2 pi minus pi over 2 minus pi is equal to 1. We don't need to put parentheses, but this should help you better understand. Actually, I put the parentheses on. I'm very bad at math, if you guys didn't know that. I'm just faking it. Once again, put the parentheses right there. Next thing, starting back from looking at my Google Docs. This one is very obvious. True written in binary. Just 1. You guys all know this. 1 0 1 0 0 1 1 0 0 1 1 1 0 1 0 0 1 0 0 0 1 1 0 0 1 1 0 1 0 0 0 1 1 0 0 0 1 1 1. It's binary. 1 is true, 0 is false. I don't think I'm ever going to use that. So there we go. True and binary is equal to 1. Integrate a cosine function from 0 to pi over 2 is equal to 1. Look at this. This one. All right. So integral cosine is sine, right? Secant sine or negative sine. I know that. So sine x from 0 to pi over 2. So sine pi over 2. You just plug in that for x. It's equal to 1. Boom. Very simple. And if you do this from negative pi over 2, it'll be equal to 1. So here we go. Same thing. All right, find the Taylor series of a function, and then plug in x to get 1. So let's find the Taylor series of 1 over x. So we know that the Taylor series formula is equal to the infinite sum of infinity to n equals 0 of fn x times a of n factorial x minus 1 to the nth power. That is the formula to get a Taylor series. Anyways, let's find the Taylor series of 1 over x. Taylor series of 1 over x. So let's first find the derivative of x. So 1 over x is equal to x to the negative first. So the derivative of f of x. So f of x is 1 over x. Just screw that up. It's equal to negative x squared. F double prime x is equal to 2x negative 3. F triple prime x is equal to 6x negative 4. Anyways, let's calculate the Taylor series for that right now. Now that we have a couple derivatives, so I can't write that over. Approximately equal to So we're just gonna go with the basic so x negative 1, and we're gonna center that a is equal to 1, just to simplify the calculations. 0 factorial, once again, 1. In fact, that's where I got the idea from. X minus 1, 0, plus negative x squared over 1 factorial. That's also 1, but don't worry, I did not use it in my list because that's very obvious. But 0 factorial is less obvious. Oh, but this is supposed to be a. I was already going to center a, that's why I got 1. That's why I wrote that there. But that's why I'm putting 1 in here because a is equal to 1. So yeah, there you go. Alright, oh, by the way, I should be plugging in 1 for these. Because a is 1, so I plug in for x right here, but not the x in there. That's where we're going to plug in x equal 1 to equal 1, because 1 over 1 is 1. X equals shattering. So 1, this is supposed to be negative. So 1, negative 2 is, so this is negative 1. Hold on, I want to go with my work. 1, negative 1, 2. Alright, so now, I should be writing this out right here. 1, negative 1. I'm supposed to be getting rid of the exponent. Plus 6 over, wait. Oh, this is no. This is supposed to be 1 because playing this x negative 1 is stupid. Oh, what? That's 1. Then this is also 1. And this is negative 1. Negative 1. 1. Squared. Factorial. We have. I think. Negative 1 here. Then 1. Here. Nice. Screw it. Right here. Oh my god. That's negative 1. Yes. Right out. This is negative 1. And this is supposed to be 2. This is supposed to be 6. There we go. That's right. No. That's a pi. Alright. So now, let's simplify this. So this is going to be equal to x minus 1, or just x minus 1. I'm not going to simplify the x1 because I'm going to need that to determine how the Taylor series is selected. Alright, so now it's going to be 1, plus x minus 1 first power, so it's going to be 0, so it's going to be minus 1, plus minus Alright, we have the simplified version. So that means that 1 over x is equal to the infinite sum, and is equal to 0. And just so you know, it starts off positive, so we're going to use negative 1, and because at the end, so we're going to have negative 1, n times x minus 1, n. Alright, so if we plug in n is equal to 0, so negative 1 to 0 is 1, just so you know. So negative 1 is 1, it's going to be positive, and it's going to be, we start at 0, then it's going to go to negative 1 to the first power, which is negative 1, so it's going to be negative n to the first, and it's going to keep cycling to that. Alright, so we successfully found the Taylor series from 1 over x. Alright, so now we're just going to simply plug in 1 for this. So we're going to have 1 minus 1 plus 1 minus 1 to the first plus 1 minus 1 squared minus 1 minus 1 to the third. So this is going to be, by the way, depending on this is going to be infinite. We already solved for this, so don't worry. But this does get, if it goes on infinitely, so it's impossible to determine whether or not it's going to be positive or negative is equal to 0. So 1 minus 1 is 0. Actually, no, it's 1. This is the 0th power, so 1 minus 1 is 0. The 0th power is 1 plus 0 plus 0 plus 0 infinitely. I was wrong about that. So there we go. 1 over x, according to the Taylor series we found, is equal to 1. I mean, 1 over 1, according to the Taylor series we found, is equal to 1. Anyways, yeah, that's that. Okay, that is true. 1 over 1 is indeed equal to 1. Alright, here comes the stuff that you don't normally think of. The first x-intercept of sine of x minus 1 is equal to 1. Let's look. So we have the plane, then we have and this is sine x minus 1. This point right here is going to be equal to 1, 0. This makes sense because, you know, if you're rusty, 0 is the output. So if you plug in 1, so sine 1 minus 1 is equal to 0. So the output is 0. So therefore, the x-intercept is going to be 0. Let's move on to the last one. Any number, wait, hold on, let me try this out. N plus 1 divided by, hold on. Any number, so n plus 1 divided by n, the remainder will always be equal to 1. And let's see this. So let's do 55 divided by 54. 54 goes to 55 once, 54, and the remainder is 1. Alright, there you go. Something that you never really think about, but it's very, very easy to grasp. This works for any number. And just, you know, if you guys have any ideas of anything that I missed, please let me know on top of suggesting music. Next video, we're going to be focusing on putting all this stuff into our main equation. So look forward to that. Anyways, make sure to suggest some music. Suggest another ways that equal to 1. Don't make it something stupid like 248,444 minus 248,443 is equal to 1. Like, it has to be like generalized stuff, like I said, that can work for a wide range of numbers. And I'd love to see what you guys have to come up with, and I'll do my best to get it to work at the end of next video. Anyways, guys, I hope you enjoyed. Make sure to like and subscribe, and well, if you like math, and if you enjoy what I do here on the channel, please make sure to like and subscribe, comment, because I love reading your guys' comments. All the cliche, you guys know it. Suggest music down in there, share to the channel, and I got to go. Goodbye, everyone.